Hello everyone. So in our yesterday's lecture we have understood how to represent floating point numbers in binary and floating point numbers. We have also seen how to represent fixed point numbers and floating point numbers in binary. Now we'll continue with the same lecture with the same topic. So let's have one more example which will help us understand. Let's say if we are given with a floating point number in binary, then how to convert it back into decimal number. Along with that, we'll also in this lecture we'll also learn about various other aspects of floating point numbers and how to increase the precision, decrease the precision, and many other things. Let's see. So let us say we have a floating point number which is represented in binary. Now we would like to extract what is the decimal number it represents. So I'm taking it as an example. So let's say for example, the floating point number is 0 cross C263 4 zeros. So if such a number is given to us, then how to start? First we will represent this hexadecimal number into binary. Okay, in binary we'll again further make the groups of 4. So the group of 4 means like we'll break it into nibbles so that it's make things easy. So first is C means 12, and then the next nibble is 2, next nibble is 6, and the next nibble is 3, and the rest of the 4 nibbles are 0. Now we know now the binary notation of this floating point number. From our previous lecture, we understand that each binary representation would have exponent, sign, and mantissa. And we also know that the 31st bit in a 32-bit number is going to represent sign, and next 8 bits, that means 1 0 0 0 0 1 0 and 1, this part would represent exponent and the rest is mantissa. So I'll write all of these things separately. Sign is 1 and exponent is 1 0 0 0 0 1 0 and 0. So if I put this in decimal, this become 128 plus 4. So how do I find 128? This is the weight of this number is 1, this is 2, this is 4, 8, 16, 32, 64, 128. So 128 plus 4 is 132. So the actual exponent, we have to reduce the offset also, which we were adding to represent the negative exponents. So the actual exponent is, this is the exponent which we have written in the floating point binary number, but the actual exponent we have to subtract the offset. So in case of 32-bit binary, 32-bit floating point number, offset is 127. So let us subtract this 127 from 132, remaining is 5. So rest of the bits, rest of the how many bits? 23 bits. So rest of the 23 bits are mantissa. So in mantissa we'll write it from here 1 1 0 0 0 1 1 and then rest of the zeros. So remember, when we were converting a binary number or a decimal number to exponent, then we first had to have, first we were having significant, then we were extracting mantissa. So the same step will go in as a next step here. So actual, this binary number, I can write it like this: 1 is a significant which I need to add. So the significant would be added, and then I'm writing the mantissa bits. I'm skipping all the zeros because they don't count. So all the non-zeros, all the trailing non-zero numbers I am adding. So that means 1 1 0 0 0 1 1. So and exponent I got as 5. So into 2 to the power 5. So this is the binary number. We can represent, or this is the scientific notation of this floating point number. So this floating point number has this binary number as a notation. Now what is the next step? Because this is 2 is to power 5, so let me multiply 2 is to power 5 to this number. So what it will become? So that means this decimal point would be shifted by 5 points. 1, 2, 3, 4, 5. So this decimal point would be shifted here, and I can rewrite this number as 111,000 decimal point 11. So now I can create the decimal number, which is 32 plus 16 plus 8 plus 0.5 plus 0.25. So this is 1 by 2, this is 1 by 4, and adding all of them will give me 56.75. So this is how would be a general procedure if I have given I came to know about a floating point number which is represented in hexadecimal or in binary. Then I have to go this step by step, first extracting sign, exponent and mantissa, and then recreating the binary number, and from there I will create the decimal number. Good. So with this, now we understand how to convert a decimal number to floating point number, floating point number to decimal numbers. Now let us see. The motivation of these decimal numbers, motivation of these floating point numbers was twofold. One, I would like to represent fractions. The second thing was I wanted to represent very large numbers as well as very small numbers. So let us try to see that if I want to write or want to express the largest number or large number, how much large it can be if the notation is that these 32-bit floating point numbers. So for the largest number, the exponent range for this floating point numbers, for 32-bit floating point numbers, are actually 8 bits are assigned. So 8 bits means 0 to 255. But in previous lecture we have stated one fact that 0 and 255 is not allowed. So that means they are reserved. So let us not use them. So the maximum exponent we can have is 254, and the minimum exponent we can have is 1, not 0. So we'll see why 0 and 255 are reserved. So that would come. Now the largest exponent is 254, and if I want to write the maximum number, certainly the exponent has to be the largest, that is 254. And what about mantissa? So mantissa, if all numbers are 1, all bits are 1, so that would represent the highest number. So if I write all the ones and will also add the significant part, so the number will become something like this: 1 point, all ones in mantissa, like there are 23 ones, and then 2 is to power 127. So why this 127? Because I have reduced or subtracted my offset of 127 from 254. So the value is 254 minus 127 equal to 127. So if I compute this, if I see this really close, so this is 1.1111 up to 23 bits. So that is very, very close to 2 actually. So if I expand this, what does it mean? This is 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 plus 1 by 32 plus 1 by 64 plus 1 by 128. So this is geometric progression. So, and in the geometric progression, if I would like to calculate the sum, it would be equal to 2. So that's how it is, approximately 2 is to power 128. Okay, so actually 2 got multiplied with 2 into power 127, so we will finally have 2 is to power 128, which is approximately equal to 3.4 into 10 is to power 38. So which essentially means that around 10 is to power 38, so there are 38 zeros at 1 before 1, so that much large number I can represent in single precision floating point numbers. And how many decimal digits? So because my mantissa represent around 23 bits, so approximately 7 decimal digits could be there as a fractional part in any of the scientific notation. So What about the smallest number? In case of smallest number, my exponent would be 1. Because exponent is 1, so the real exponent will be 1 minus 127. That means minus 126. Mantissa bits, all of the Mantissa bits would be 0 because I am trying to find out the minimum number. Okay, the number can be represented as 1.0 into 2 to the power 126 minus 126, and this comes to be around 1.1 into 10 to the power minus 38. So this is the smallest number. So this satisfies a good fraction of number that we see around. So precision is around 7 decimal digits, and maximum number is 10 to the power 38 and minimum is 10 to the power minus 38. A reasonably good number of numbers can be represented using this single precision floating point number. Now what about 0? So if I put exponent and mantissa both as 0, the positive, there would be two zeros, one is positive 0, another is negative 0. So in our one of the previous lectures, when we were discussing negative numbers, we were highly objecting this thing that there shouldn't be two different notions of zeros. But here we are accepting this fact that 0 will have two different notions or two different representations. Why? Let's try to understand this thing using a line, using a number line. Okay, so number line is a horizontal line which would say that, let's say we'll have a 0 starting from this, and then the numbers are keep on increasing in the arrow direction. Okay, so if this number line represent what kind of numbers can be represented using single precision floating point number, then we can see that there is a discontinuity. So the smallest number that can be represented is 1.1 into 10 to the power minus 38, and the largest number is 3.4 into 10 to the power 38. So what does this mean? Try to understand this, that this number 1.1 into 10 to the power 38 is very close to 0. Because it is very close, it can be approximated to 0 also in certain scenarios. But still, the fact remains that there is a discontinuity, that we cannot represent any number smaller than 1.1 into 10 to the power minus 38. Similarly, this is also a fact that any number which is larger than 3.4 into 10 to the power 38, that cannot be represented using this particular notation of single precision. So there would be kind of an overflow. How do we represent overflow? That is also one question which we need to answer. Similarly, this line, number line, can also be extended in the negative direction. So in the negative direction also, there would be the smallest negative number is minus 1.1 into 10 to the power minus 38. Again there is a discontinuity, and the largest number is 3.4 into 10 to the power minus 10 to the power 38. So there is a negative sign here, we will correct this. So now you see that the number which is smaller than 10 to the power 38 and larger than 0, what should it be called? Because that number is very close to 0, we can call it positive 0. It is more than 0 but lesser than 10 to the power minus 38. So that's why we can call it positive 0. So the positive has a certain meaning here. Positive certainly says that the number is more than 0 but it is less than 10 to the power minus 38. So that will have at least some meaning. So either it is completely 0 or it is slightly more than 0 but less than 10 to the power minus 38, which cannot be represented in the normal representation. Similarly, there could be a negative 0 also. The number is smaller than minus 10 to the power minus 38 but more than 0, because it is more than lesser than 0 but more than this. So that means there is a discontinuity. This number would be represented as negative 0. That means 0 cross 8, 7 zeros in hexadecimal. So what we call a number which is larger than this? 10 is for 38. 10 is for 38 itself is a very large number. If a number is even larger than this, what should we call this number? Can we call that infinity? Yes. So there could be now two infinities. One is a positive infinity, the other could be negative infinity. Any number which is larger than the number which can be represented using single precision numbers is positive infinity. In the similar way, any number which is lesser than the largest negative number is a minus infinity. So this is the way we can understand that what kind of numbers can be represented using single precision floating point number. Now there is one interesting website which tells a little more interesting facts about this. This is called this is a very nice web browser. This browser hsummit.net float converter IEEE 754. So this browser, this website gives quite a good intuitive information that what kind of numbers can be represented, and we can play around a little bit. So I'll give a small demonstration of this website. So we can see here that you can write the numbers in any form. So let's say I would like to write the number in decimal. So in decimal I say, let's say the number is 1000. I press the enter button. As soon as I press the enter button, it says that your number is 1000 in decimal, and after that now binary representation is this. And the beautiful thing is that along with the binary representation in this form, it also breaks things into sine, exponent and mantissa. So it says your exponent is there is this bit is high and this bit is high, and similarly in the mantissa also it specifies that what is the mantissa. Okay, and this part is essentially significant. 1.95312 is a significant part. So similarly, this is the hexadecimal representation. Now I can play around with that. I can say that this, I can toggle the bits, it become a negative number, or I can also see what is the largest number. So in that case I will make all of these bits as 1. Okay, and so I have to keep this as the minimum bit. 254 is the maximum decimal. So if I say let's say if I put the maximum exponent as 255, then it says the number is infinity. However, for the 254, this is the number which is being represented. The decimal number is 1.7 into 10 is power 38. Now if I keep all the mantissa bits as 1, so that means I have to write all of this as F. Okay, one more. Yes. So this says this is the largest floating point number which can be represented using single precision numbers. Now similarly, let's see what would happen if I want to represent the smallest numbers. In the case of smallest number, all of these would be 0. So I want to say all of these are zeros, and I also would like to say that my exponent is only 1. You can see the range of numbers which are being reduced. So you can see that if this is the smallest number, this number can be represented something like this. Okay, now this is a positive number and this is a negative number. So this calculator is an interesting tool to play around with the numbers and to see that how we can convert one decimal number into floating point number or vice versa. Okay, so with this demo we can again move forward and look at some more examples, more questions. So now we will talk about these reserve bits. We said that two reserve exponents, one is 255, another is 0. So when exponent 255, that means all bits of my exponents are 1. We have seen in this converter also, and we have discussed a few minutes before that the number represents infinity. And it represents infinity only if mantissa is 0. So that means all bits of mantissa is 0, then only it represents infinity. One more number we need to represent, that is called not a number. So consider this situation. Let us say you want to divide certain number by 0. What is the result? You have been told in your primary classes, secondary classes, the number has to be infinity. But now let us look at from a very close perspective. You understand that whenever you are writing 0, this number 0 means the number is smaller than 10 is power minus 38 but more than 0. Now since you are dividing this number, dividing any number by 0, that means that this particular number could be anything. Here most likely we can call it infinity because the number would be more than 10 is power 38, so it cannot be represented. So but let us say the other case, 0 by 0. So 0 by 0 is undefined because your upper numerator is also smaller than 10 to the power minus 38, your denominator is also smaller than 10 to the power minus 38. You don't know what would be the output of this division. Similarly, if you multiply infinity with 0, what is the output? Infinity by 0. Infinity means it is more than 10 to the power 38 and 0 means it is lesser than 10 to the power 38. If we multiply these two numbers, we don't know what is the output. So this kind of scenario is called not a number. We don't know. These undefined scenarios. So in these cases of undefined, we have a special representation that a mantissa will be not equal to 0 and my exponent is equal to 255. So this represents a special scenario which means not a number. And in this not a number, there is also one more special category which is called signaling NaN and non-signaling NaN. So that means if you want to raise an error, you want to raise an exception, then the most significant bit of your mantissa is turned out as 1 so that it signals that there is an error. Okay, so that's why we have reserved this 255 as a special exponent just to represent all the infinity or not a number cases. Now what if my exponent is 0? If my exponent is 0 and mantissa is also 0, we say the number is 0. And if exponent is 0, mantissa is not equal to 0, then it is a very special case. We call it D-normal numbers. So these D-normal numbers are not supported by all systems, they are not supported by all processors, but if some particular processors are supporting it, then its meaning is slightly different from all other numbers. So in all other numbers, whenever we are trying to represent, we simply say this formula that minus 1 is power s and then p and then 2's power whatever exponent was written minus 127. Here because exponent is written as 0, we will write it directly as 2's power minus 126. And the leading one here, we remember that in significant, this number represents significant as well as so this number p represents significant as well as mantissa. Here significant is turned out to be 0 and the mantissa is added. So, and mantissa we always say it is less than 0 and 1. So that is why this particular d normal numbers, because their calculation is different, so they are classified as a different numbers. They are not normal numbers. And further, because of this additional complexity, some of the computers also do not support these d normal numbers. So these numbers are of course smaller than the smallest normal number. So they are smaller than the smallest normal number, and they are smallest than the smallest normal number, but still larger than 0. Okay, so if I keep on going like this, the smallest d normal number is equal to 2 to the power minus 149. So that also we can check from here. So let's say the number is this. If I want to say this, so these are all lesser than 10 to the power minus 38. This is 10 to the power minus 39. Similarly, if I can keep on going like this, all these numbers are lesser than 10 to the power minus 38. So let us say only the last bit is 1, rest all of these bits are 0. The smallest number which I can represent is 10 to the power minus 45. Okay, or which is also we can say 2 to the power minus 149. So this is the smallest number which we can represent even if we take into account d normal numbers. Okay, so this was about d normal numbers. Now we can take some example also. The smallest smallest normal number is 1.0 into 2 to the power minus 126, and let us say because the number is smaller, I can represent it using 0.00011 into 2 to the power 126. You see, there is no preceding 1 because the number is not normal. And why there is no 1? Because it cannot be represented within the limit of normal numbers in my single precision floating point number. So the sign is 0, mantissa is 00011, and after that all zeros. Exponent, we clearly said d normal numbers, exponent is 0. So I can represent this number again. I can collect all the bits and the number can be represented using 0000, again 0, again 0, and then 1100. So similarly, if I need to represent any other d normal numbers, I can represent that number in my floating point notations. So this explains us that what is the smallest thing which we can represent, or how this exponent 0 can become a very special exponent, and it can be used to express even smaller number. But you see, there are two side effects. One, the precision will reduce. In all other normal numbers we will have a precision of 23 bits, but here precision will keep on reducing. So let's say I want to represent some number as small as 2 to the power minus 149. Now the precision is only single bit, no more than that. So that is also one of the side effect of representing d normal numbers. Plus I have to do a separate calculation, a different kind of calculation. The offset method is not working out here. Okay, so with this let us move on to the other topics or other questions. So what would happen, let's say I have lot of d normal numbers, or lot of numbers which are lesser than 10 to the power minus 38, or if I have more numbers which are more than 10 to the power 38. I want to represent mass of universe, or I want to do something which involves very, very large numbers. Or let's say we have a third scenario also, that the precision of 7 decimal digits is not sufficient. What should we do? So in that case, what we would like to do is, we would like to increase the number of precision bits. So instead of 23 bits, there has to be more bits to represent precision. Plus, exponent also should be represented with more than 8 bits, so that larger number or more numbers can be included, or a larger size can be included.